force of attraction that exists between any two masses which is separated by a distance, and the expression is given by Newton, and very famously it is called as Newton's law of gravitation. The velocity of Jupiter when it is travelling around the sun in a circular orbit is 13.1 into 10 power 23 km per second. 2 into 10 power 30 kg. The mean distance between them is 7.8 into 10 power 11 meter. Hello everyone, welcome to session 4 of chapter 8 Gravitation. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. In this session, we are going to solve few numericals based on the expressions what we have come across from the chapter Gravitation. So here is our first problem. We have two spheres whose masses are 20 kg and 10 kg and they are 20 centimeter apart. We need to calculate the force between them. We know the force of attraction that exists between any two masses which is separated by a distance, and the expression is given by Newton, and very famously it is called as Newton's law of gravitation. The force of attraction between any two masses is nothing but G m1 m2 divided by r square. Here in this problem, we have two masses. Say for example, mass m1 is 20 kg and m2 is 10 kg and they are separated by a distance of 20 centimeter. So in meters we can write it as 0.2 meters, and we have to calculate force. Here they have even given the value for universal law of gravitation, that is G is equal to 6.6 into 10 power minus 11. So making use of all these data, let us calculate the force now. So that can be calculated as F is equal to 6.6 into 10 power minus 11, that's the value of G, into M1 is 20 kg into M2 is 10 kg divided by r square. R is nothing but 0.2 meter, or you can even write it as 20 into 10 power minus 2 meter. So let us substitute the value of r, that is 20 into 10 power minus 2. We have r square, so it is the whole square, and here minus 2, the whole square is minus 4. We have minus 11 in the numerator. So this minus 4, when it goes to numerator, it becomes plus 4. So minus 11 plus 4 is minus 7, and the answer of force that exists between two masses is 3.32 into 10 to the power minus 7 Newton. Since we are calculating force, the unit is Newton. We should not forget mentioning the unit in any of the quantities. So we'll move on to the next problem now. Here we have the second problem. Find the acceleration due to gravity at a point 64 km above and 32 km below the surface of the earth. Given that the radius of the earth is 6400 km and acceleration due to gravity on the earth's surface is 9.8 meter per second square. So in the last sessions we have come across the expression, or we have even derived the expression for the acceleration due to gravity above the earth's surface and below the earth's surface. Now we know the final expression. With the help of that, we need to find the value of G, that is 64 km above the earth's surface and 32 km below the earth's surface. Say for example, let us consider earth of mass m. So we have to find the acceleration due to gravity at this point, which is 64 km above the earth's surface, and this is h, and 32 km below the earth's surface, I'll call it as d. And the radius of the earth's surface is given. Radius is nothing but 6400 km. Acceleration due to gravity on the surface of earth is 9.8 meter per second square. So what is the formula to find the acceleration due to gravity above the Earth's surface, it is gh is equal to g into 1 minus 2h divided by r. So let us substitute all the values in this expression. So g is 9.8 into 1 minus 2 into, what is h value? It is 64 kilometer divided by the radius 6400 kilometer. So solving this, we will get 9.604 meter per second square. Since it is acceleration due to gravity, the unit is meter per second square. Now let us find the acceleration due to gravity below the Earth's surface, that is gd is equal to g into 1 minus d divided by r. So gd is equal to 9.8 into 1 minus, what's the depth? It is 32 divided by 6400, and the answer here we will get after solving this 9.751 meter per second square. Again, we are finding the acceleration due to gravity below the Earth's surface, and hence the unit meter per second square. So this is how you have to make use of the derivations or the expressions what we have studied in our theory part in finding the answers for the given question. So let's move on to the third question, that is about escape velocity. The escape velocity of a body from Earth is 11.2 km per second. Find the value of escape velocity of a body on the surface of Mars. Here they are asking us to find the escape velocity of an object from Mars surface. We know the escape velocity is different for different planets. So on Earth it is 11.2 km per second. Now we need to find on the surface of Mars what is the escape velocity, and it is given that Mars has a mass of 1/9 and radius of half that of the Earth. So the mass of the radius is 1/9 time the Earth, and the radius of the Mars is 1/2 or that of Earth, which means the half of the Earth. First let us write all the given data, then we will find the relevant answer. So escape velocity of Earth, that is VE, which is equal to 11.2 kilometer per second. So we need to find escape velocity on Mars. It is given that mass of Mars is 1/9 time of mass of Earth, and radius of Mars is equal to 1/2 the radius of Earth. So these are the given data. Now what is the formula to find escape velocity? So escape velocity formula is root of 2gm divided by r. It is, we have already learnt how to arrive at this expression in the previous sessions. Now we have to find the velocity on Mars, which means this formula is modified as 2g mass of Mars divided by the radius of Mars. So now let us make use of the data here and substitute here. We will get velocity on Mars is square root of 2g. Mass of Mars is 1/9 times the mass of Earth. So I can write it as m divided by 9 divided by radius of Mars is 1/2 times the radius of Earth. So I can write it as r divided by 2. R is nothing but the radius of Earth, m is nothing but the mass of the Earth. So I can write it as Vm is equal to square root of 2gm divided by r, and if we take the reciprocal we will get 2 divided by 9. So what is square root of 2gm divided by r? It is nothing but the escape velocity of Earth. So I can write this as Vm is equal to escape velocity of Earth and into square root. Since square root is belongs to both these two as well, so I have to write root of 2 divided by 9. But what is velocity or escape velocity of Earth? It is 11.2 km per second. So I can write Vm is equal to 11.2 into square root of 2 divided by 9. So square root of 2 divided by 9 into 11.2 give us 5.280 kilometer per second. So this is the escape velocity of an object from the surface of Mars. So let's move on to the next problem. The mass of Jupiter is 1.9 into 10 power 27 kg and that of Sun is 2 into 10 power 30 kg. The mean distance between them is 7.8 into 10 power 11 meter. Find the gravitational force exerted by the Sun. Jupiter also has got some mass. Sun has also got some mass. So there is a force of attraction between these two mass, and we have to find the gravitational force that exerted by the Sun on the Jupiter. And also we have to calculate the speed of Jupiter assuming circular orbit around the Sun. We all know that the Jupiter or any other planet that revolves in an elliptical orbit around the Sun, but here we have to assume that Jupiter is circular in orbit around the Sun. So first let us write the given data. Here the mass of the Jupiter, I will take it as m1, which is equal to 1.9 into 10 power 27 kg. And the mass of the Sun, I will take it as m2, which is equal to 2 into 10 power 30 kg. And the distance of separation between them, that is r, is 7.8 into 10 power 11. We need to find the gravitational force that exerted by the Sun, and hence the formula F is equal to G m1 m2 divided by r square. What's the value of G? It is 6.67 into 10 power minus 11 into m1 is 1.9 into 10 power 27 into m2 value is 2 into 10 power 30 divided by r square, that is 7.8 into 10 power 11 the whole square. So solving this, we will get 4.16 into 10 power 23, that is the force we are calculating, and hence the unit Newton. Here we have to assume that the Jupiter is circular in motion around the Sun, and hence F provides the necessary centripetal force for the Jupiter. So the centripetal force is given by mv square divided by r, as we all know the expression. Now we have to find the speed of Jupiter. So speed of Jupiter can be calculated as v square is equal to, multiply these two, we will get F into r divided by m. But we need just the value of v, and hence we have to write square root of F into r divided by m. So here m is nothing but the mass of Jupiter, so I have to take it as m1. So let us now substitute all the values. So v is equal to square root of F value is 4.16 into 10 power 23, and r is nothing but the distance of separation, that is 7.8 into 10 power 11 divided by m1 is 1.9 into 10 power 27. So solving this, we will get the value of speed of the Jupiter, assuming that the Jupiter is in circular motion around the Sun, and the value of v is calculated as 13.1 into 10 power 23, and since we are calculating the speed, the unit is kilometer per second. So the velocity of Jupiter when it is traveling around the Sun in a circular orbit is 13.1 into 10 power 23 kilometer per second. So let's move on to the next problem. If the distance between the Earth and Sun were half its present values, what would be the number of days in a year? So the question is quite interesting. If the distance between Earth and the Sun is half of its present distance, what would be the number of days in a year? See, without any data, we can calculate the answer for this question by having a knowledge of Kepler's law of planetary motion. So which law we have to take into consideration here? So it is talking about the number of days, which means, and also they are talking about the distance between Earth and the Sun, which means the law which satisfying these two conditions is, which states that the square of period of revolution is directly proportional to cube of its semi-major axis. So let's make use of this condition for both Earth and Sun, and we will write it as T1 by T2 the whole square is directly proportional to R1 divided by R2 the whole cube. And it is clearly given that if the distance between them is half of the present value, so we can write it as T1 divided by T2 the whole square is directly proportional to R1 divided by R2 is nothing but the distance after the modification. R1 is the present distance, so it becomes half of the present distance. what is the number of days. So when R2 becomes R1 divided by 2, what would be the number of days in a year? We have to calculate. So solving these two, R1 divided by R1 by 2, the whole cube. So you will get T1 divided by T2, the whole square is equal to, so solving the above expression, this will be equivalent to 8. So we want T1 divided by T2, the whole square is equal to 8, but we need what would be the number of days. So we can write this as T1 divided by T2 is equal to square root of 8, and we can write it as T1 by T2 is equal to 2 root 2. And we have to calculate the number of days, that is time period T2 after the distance modification. So we need T2, which will be equal to, we can rearrange this, T1 divided by 2 root 2. What is T1? The time period now, which means the number of days without any modification or in the distance between Earth and Sun. And it is 365 days we have divided by 2 root 2. So what is the value of 365 divided by 2 root 2? If you find, you will get the value of the number of days after the distance becomes half of the present value, and the value of T2 is equal to 129 days. So from this we can say that if the distance between Sun and the Earth becomes half of the present value, the number of days would be 129 in a year. Instead of 365 days, we would be having 129 days in a year if the distance becomes half of the present value. So these are the few examples from the chapter Gravitation. In the next session, we'll discuss about another new chapter. Until then, all of you keep learning. Take care. Thank you.